Lesson 1-3, Extrema and End Behavior. What do they mean by extrema? Graphs of functions can have high and low points where they reach a maximum or a minimum value. The maximum and minimum values of a function are called extrema. The maximum is at the highest point of the graph of a function, and the minimum is the lowest point. But there are also some relative maximums and minimums. A relative maximum is located at a point on the graph of a function where no other nearby points have a greater y coordinate. It doesn't mean it is the highest point, but it is a high point at some point in the graph. So an example like that would look like something like this. This point right here is a high point, but that's not the highest point on the whole function. So that would be considered a relative maximum. A relative minimum is located at a point on the graph of a function where no other nearby points have a lesser y coordinate. So if I have this point here, which is a low point, it's just not the lowest point because it keeps going down lower on the left-hand side. So that would be a relative minimum. Let's take a look at some examples here. It says identify and estimate the x and y values of the extrema, round to the nearest tenth if necessary. So here I have the lowest point right there. So this would be a minimum. There is no other low point, so this is a regular minimum, and we would say the point is at 0, -5. We wouldn't consider that the relative minimum because there isn't a lower point than that. So we would just consider this as just a minimum. Letter G, for g of x, we have a minimum here. And actually, that's a relative minimum. And the reason for this to be a relative minimum because it does go lower later on. It just means this is a low point. This would be 0, 4. And then we have a relative max. And the relative max here would be 0, or not 0, -2, 8. And that would be a relative max because we do have a high point. We just don't have a regular maximum because we don't know it goes on to infinity. So this would be just a relative max and a relative minimum. Next, use the graph to identify the extrema of this function. We have quite a few here. There isn't a maximum because it goes to positive infinity, but there is a minimum, and we do have some. We could consider some of these to be relative minimums. So, but we have one minimum, and so let's do it this way. Max, we have none. Minimum, like the lowest point is right here, and that point would be -6, -7. Now with the relatives, so we have a relative max. So we have some high points, just not the highest point. We have one here, which would be -3, 2. We also have a high point here, which would be 2, 6. And then we have a relative minimum. It means a low point, just not the lowest point. We have one here, which would be 0, -4. And we have one here, which would be -5, or 5, -5. Example 2, use the table and graph to estimate the extrema of the function that relates the number of hours since midnight x to the number of posts being uploaded y. Describe the meaning of the extrema in the context of the situation. So the extrema, the highest point. We do have a high point here. We do have a high point here. We have a low point here. we also have a low point here as well. So let's go from left to right. So here we have a relative minimum. And it's a relative minimum because it does go down based on what we see on the right-hand side. So we have a relative minimum. Actually, that would probably be the lowest point. So we could have that. We'll just make that a minimum. So that would be 4 hours. So at 4 hours, you would have roughly 1.8. And since that number is in the thousands, 1.8 would mean like 180,000. So 4 hours. So I would let's say 4 o'clock, 4 a.m. There was 180,000 posts. Now the maximum, the highest point is right here. That means 12 hours. 12 hours after midnight would be noon. So at noon, there was, that's halfway, so 11 and a half. So 11.5, so that would be 11 and a half. Let's do, that would be like 1,150,000 posts. Then we have a relative minimum. And the relative minimum would be here. So we could say 14 and 9. So 14 hours after midnight would be 2 o'clock. So 2 p.m. And at 2 p.m. that was roughly, we could say like 900,000 posts. And if we looked at here, they had 9.1. So let's do, that'd be 910,000 posts. And then we have this point here, which is a relative max. And that was 16 and 10.2. So 16 hours after midnight would be 4 p.m. And they would have 10.2, so that would be 1,020,000 posts. Next part. During the trampoline event at the Summer Olympic Games, athletes perform acrobatics while jumping on a trampoline. The graph shows the height of an athlete above the ground while performing a somersault. Use the graph to identify the extrema of the function and what do the extrema represent in the context of the situation. So let's first deal with maximums. So the highest point. Do we have any highest points? We do have the highest point right there. So we would say that would be 4 and halfway, about halfway, or just under halfway from 27 to 30. So let's just consider that 28, so 428. Then the minimum, the lowest point would be right here, which that would be 6, and we could say that would be roughly 1.5. So 6 and then 1.5. Then relative max. So high points, just not the highest points. That would be 2 and 12. And that would be 7 and we'll make that 21. And we have 9 and 6. and relative minimum, so some low points, just not the lowest. That would be here, so let's do 0.53. We would have 3, 3. And we would have 8, 3. Now, what do these extremas mean? Instead of doing the each individual one, like the minimums would be the least height, and the max would be the greatest heights. That the acrobat had gotten while performing. The next part of our lesson is looking at end behavior of functions. What do they mean by end behavior? End behavior is the behavior of a graph as x approaches positive or negative infinity. So when you think of end behavior, think of the arrowheads. Where are the arrowheads pointing? Is it pointing up? Is it pointing down? As you move along the graph, the values of x are increasing towards infinity. This is denoted as x, and with the arrow, we would say x approaches positive infinity. At the left end, the values of x are decreasing. So when you go left, you're decreasing towards negative infinity. And we would say, denote that as x with the arrow approaches negative infinity. When f of x, which means your y, increases without bound, without any restrictions, is denoted as f of x approaches positive infinity. You could also use y if you wanted to instead of f of x. And then when the function f of x decreases without bound, means it goes to the left. Or when it keeps going down, it's denoted as f of x equaling negative infinity. So an example, it says describe and compare the end behavior of each linear function. So we would write the statements as x approaches, so if I go to the left to negative infinity, f of x approaches, so when I go to the left, the arrow is going upward, so that would mean positive infinity. And as x approaches positive infinity, f of x, so when I go to the right, the arrow is going downward, so it approaches negative infinity. For b, for g of x, we would have as x approaches negative infinity, so when x goes to the left, the arrow, where is the arrow going? F of x is actually equal to 2. It still stays 2. And as x approaches positive infinity, so when I go to the right, f of x still equals 2. So there we wouldn't have it. It goes to positive infinity or negative infinity because it stays the same. Next, use the graph to describe the end behavior of the function. Let me go back to that previous one here. We've got to compare the end behavior of each function. F of x is not bound, which means there isn't any boundaries. It continues to go to infinity. But for b of x, there is boundary. There is restrictions. It only equals, or f of x only equals positive 2. So that would be the difference between the two functions at the end behavior. Now back to this one. Here we would start our statements, and the statements always start the same way. As x approaches negative infinity, when x goes to the left, where does the arrowhead go? The arrow is pointing downward, so f of x would approach negative infinity. And as x approaches positive infinity, when I go to the right, where's the arrow pointing for f of x? F of x approaches, it's going upward, positive infinity. Next, describe the end behavior of this function. As x approaches negative infinity, so when I go to the left, f of x approaches positive infinity. Your y gets bigger. As x approaches positive infinity, our f of x approaches negative infinity. So when I go to the right, the arrowhead is pointing downward. Next, describe the behavior of these nonlinear functions. So as x approaches negative infinity, so when I go to the left, the arrow is pointing upward. So f of x would approach positive infinity. And as x approaches positive infinity, so when I go to the right, the arrowhead is also pointing up. So we would say f of x approaches positive infinity. Next one here, as x approaches negative infinity, when I go to the left here, g of x approaches, goes downward, negative infinity. And as x increases or approaches positive infinity, g of x approaches, goes upwards. When I go to the right, it goes upward, positive infinity. Use the graph here to describe the end behavior on this one. So as x approaches negative infinity, so when I go to the left, y approaches negative infinity. And as x approaches positive infinity, so when x increases, y approaches negative infinity. It decreases. This next one describes the behavior of this nonlinear function. As x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, my y decreases, so it approaches negative infinity. Example 5, determine and interpret the end behavior. So from a word problem, it says the graph shows the altitude of a drone above the ground f of x after this. Describe the end behavior of f of x and interpret it in the context of the situation. So as x approaches positive infinity, my f of x approaches positive infinity. Now I can only have that one, and the reason why I can't have approaching negative infinity when x approaching negative infinity, because I can't have negative time. And if I can't have negative time, the f of x is not going to be negative, a negative altitude. So I'm only going to have one statement here. And what this is saying, as the longer the drone is in the air, the altitude is expected to go up. Now you can see that it goes up and then comes down and goes back up and then comes back down and so forth. So the longer you're using the drone, typically it's going to go higher in the altitude. Next, Mika and her friends are using a ride-sharing service to take them to a concert. The function models the cost of the ride f of x after x miles. Describe the end behavior of f of x and interpret in the context of the situation. Now, the same thing as the last one, because of you're going to have limitations on your miles and cost. We're only going to have one statement, and that would be as x increases, our y is also going to increase. It's going to improve. It's going to approach positive infinity. And what does that mean? The more miles driven, the higher the cost. Okay, for this one here again, it's the same question here, just multiple choice question here. A, as x approaches negative infinity, f of x equals negative infinity. You said that that can't work because you can't have negative cost and negative miles. As x approaches negative infinity, you can't go to negative infinity. You're going to go higher up. That would not make sense because if I go to the left, the cost goes down, so it's not B. As x approaches positive infinity, f of x decreases. No, that's not correct. It is D. As x approaches positive infinity, x approaches positive infinity. F of x is not defined for x is less than 0. I just means I can't have negative miles and negative amounts charged. And what does that mean? We did that. The more, we can restate that here. More miles driven, the higher the cost. And our last question. The graph shows the total number of popular tablet computers sold. F of x in the time since its release, x. Describe the end behavior of the function and interpret in the context of the situation. Again, in this word problem, I can only have positive values. So one statement, as x approaches positive infinity, f of x approaches positive infinity. And what does that mean? The longer it is after the release, more tablets were sold. Now, there would become a point where if it's too old, people aren't going to buy it, you're not going to have as much. But in general, if something's being released, the years afterwards, there's going to be more of that item being sold. So that is our lesson on extrema and end behavior.